Parent functions. So our first parent function is just the constant function. You have a couple of options here. One, you could just have y equals some number. I'm going to call that number c. This is going to create just a straight horizontal line crossing at whatever c is. So to graph it, I'm going to do the example of y equals 2. For the line y equals 2, y is going to always be 2 for every possible x value. Like I said, that's just going to create a horizontal line that's constant all the way. If we had, for example, y equals 2, our x points for whatever x value you had, let's say -1, 0, 1, y would always equal, in this case, 2, or in the more general case, we'll call it c. C. Y is always going to be the same number. If we use this constant equation, y equals c, for our domain and range, remember domain is all your possible x values. Well, x could be any possible number, so remember we say that's all real numbers. For our range, we only have one possible y value. Y is always going to equal c. Now just a little side note here on functions. This one is a function, but our other constant equation would be an x equals something. Let's say x equals n. An x equation is going to create a vertical line. So for example, I'm going to draw x equals 3. X equals 3 is going to again cross where x equals 3, creating a vertical line. Now this one, like we said, is not actually a function because our x value is only one number. But if we were going to identify our domain and range, very similarly, the x values are always going to be n, and the range could be any possible number, so that's all real numbers. Again, for this equation, if we were going to list out some key points, x would always equal whatever that number is, no matter what number y would be. So those are our constant equations. We're not actually going to use those a whole lot doing our transformations, but they're still good things for you to know. Our first true parent function that we're going to be using a lot in this chapter is the linear parent function. Remember, parent functions are the most basic form of this equation. So the most basic form of a linear is just going to be y equals x. For the line y equals x, we're going to use some specific points that eventually you're going to have memorized. So we're going to start with x is -2, -1, 0, 1, and 2. Most of the time, those are going to be our x points, but not all the time. For these x values, if y equals x, then y is going to be the exact same numbers. If I graphed these points, I would create my parent function for my linear equation, which is just going to be the slanted line that goes through the origin and has a slope of 1. Domain for this graph, again, I'm going infinitely to the right and to the left, all real numbers. I can plug any value in there for x, and if I can plug any value in there for x and y equals x, then my range is also going to be all real numbers. I'm going infinitely up and down. Our next parent function is going to be the quadratic. Quadratic parent function or equation looks like this, y equals x squared. Quadratic. For y equals x squared, we're going to use the same x values, -2, -1, 0, 1, and 2. But you have to remember what your equation is to figure out what your y values are. -2 squared is going to equal +4. -1 squared, 1. 0 squared, 0. 1 squared, 1. 2 squared, 4. When I graph these, it creates a U shape for our equation. If we wanted to continue a few points, we could put a couple more on here. It would be 3, 9. So we could also graph that one if we wanted to. There are going to be many times, though, with these parent functions that point is going to be stretched off of the grid that's given to you. So sometimes it's not that helpful. Sometimes it is, though. Notice for quadratic, we have this nice U shape. Our domain for this one, again, I can plug any number in for x, and it's going to make this true. So our domain, all real numbers. Our range, though, if you notice, I only have positive y values, because the range here, if I square something, I'm going to get a positive number. So our range is y is greater than or equal to 0. Or if you prefer interval notation, you can say it's from 0 to infinity. Remember that we always use the parentheses on the infinity end and a bracket on the 0 because y can equal 0. I'd also like to point out like the symmetry of this graph. Whatever your point is on this side, you're going to have one mirrored across on the other. Cubic function is our next one. That's y equals x cubed. For this one, we're going to use the same x values, negative 2, negative 1, 0, 1, and 2. This time we're cubing it. Remember, that means a number times itself 3 times. So negative 2 times negative 2 times a negative 2 is going to equal a negative 8. Negative 1 times negative 1 times negative 1, negative 1. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. Again, graphing these equations, here's 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. Creates this nice little curved shape. For this one, again, for my domain, I can plug any possible number in for x and get a solution. So this is all real numbers. For range, this time I do have some negative values. This one's going up and down. Also all real numbers. Next page. Our next parent function is going to be the absolute value equation. This one is going to be y equals the absolute value of x. Remember those two bars. Same x values we've been using, negative 2, negative 1, 0, 1, and 2. But when I take the absolute value, remember that means the distance away from 0, so the absolute value of negative 2 is just going to be 2. The absolute value of negative 1, 1. Absolute value of 0, 0. Absolute value of 1, 1. And absolute value of 2, 2. When I plot these points, it creates this nice V shape. So on the right side of your graph, you have part of your linear equation, but on the left side, it's kind of reflected up because of the absolute value. So absolute value makes a V. Domain for this one, again, I can plug any number in for x and get a solution. So all real numbers. Let's go into the left and to the right. For our range, again, this time I'm not getting any negative values. My graph is all on the positive x-axis, or positive y values. So this is going to be y is greater than or equal to 0. Again, if you prefer interval notation, just like with the quadratic, 0 to infinity. Square root equation. This is going to be y equals the square root of x. For our x values, we're going to change it up a little bit this time. X is going to be only from 0, 1, 4, 9, and then you could put 16 if you want to, but mainly these 4 numbers. Now, why didn't we use the negative values? Remember, you can't actually take the square root of a negative number. Square root, and why did I not keep going with 2 and 3? Because those are numbers I don't know the perfect square root of. So it helps to use numbers that you do so we can have nice points for our graph. Square root of 0 is going to be 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Again, I could plot these points 0, 0, 1, 1, 4, 2, and then if I wanted to, I could plot 9, 3. Again, there are going to be many times when that point's too far to really help you out too much on your graph. I would also like to point out that these points are very similar to what we had with our quadratics. They're just kind of switched. The y and x values have switched for the square root function. For our domain, we've already pointed out the fact that I can't take the square root of a negative number. My graph is only going in the right direction. So this is going to be x is greater than or equal to 0. Again, if you prefer interval, 0 to infinity. For our range for this function, again, I'm only getting positive output. It's only going up. It's going up very slowly, but it is going up. So y is greater than or equal to 0. Again, you could use interval notation if you prefer. Reciprocal, also sometimes known as rational. This equation is y equals 1 over x. Notice x is in the bottom. Sometimes I think calling it rational helps a little bit because this looks like a ratio. For our x values for this one, we're going to switch it up a little bit too. 0, we're also going to have, we'll just go ahead and do, mainly I want you to know -1 and 1. You could put -2 and 2 on here, but the main part that's going to be helpful for graphing this one is just between those two. If I plug in a -2, what is 1 divided by -2? Well, that's a -1/2. That's why I say that one's not super helpful, because it is a fractional value and it's hard to be really accurate with halves. When I plug in a -1, 1 divided by -1 is going to be a 1, a -1. 1 divided by 0 is not possible. If you plugged this in your calculator, you would get an error. And I'll show you why here in just a minute. 1, 1, and 2, 1/2. Okay? When you look at this graph, here at 0 we have an error because the rational function has what's called an asymptote. We'll be talking about that a lot later in the year, but since there's an error here, we like to draw this little dotted vertical line because this equation is never going to equal 0. It's also never going to be able to equal 0 in this direction, since it can't ever equal 0 in the other one. This is called a vertical and a horizontal asymptote. Our next points we could go ahead and plot. Here's -1, -1, -2, -1/2. Here's 1, 1, 2, 1/2. This one is just going to create this funny little curved shape that follows along these asymptotes but never crosses those dotted lines. Same thing on this side. It's getting closer and closer to those lines each time. Hard to tell on my graph, but it never actually equals 0. But it does go infinitely to the right and infinitely to the left, but never equals 0, 0. So our domain and our range here is kind of tricky. It is all real numbers, except x doesn't ever equal 0. Same thing for our range. It goes up and down, but it never actually crosses at 0. Exponential. This one's y equals, we're going to use a more specific equation here. We're going to say that y equals 2 to the x power. Technically, this number could be any number, and depending on what that number is, the graph does a couple of different things. But for what we're using our parent functions for, we're going to use the specific case of a 2. For this one, there's only a few points I want you to know. We'll do -1, 0, 1, and 2. If I plug in a -1, 2 to the -1st power, you might need to use your calculator on this. We haven't done a whole lot of exponents yet, but you might have done some in Algebra 1. Remember that means it's 1 over. So this becomes 2 to the -1st power becomes 1 over 2. 2 to the 0 power is 1. 2 to the 1st power is 2. 2 to the 2nd power is 4. I could continue on if I wanted to. -2 would have been 1/4. 3 would be 8. But mainly, I just want you to know these points right here. Again, I could graph these. -1, 1/2. 0, 1, 1, 2, 2, 4, and if I wanted to do 3, 8, I could. This graph is increasing exponentially, but it's never actually going to equal 0. No matter how many times I make this number smaller, it's never going to equal 0 because, again, we have an asymptote here. Our domain for this one is all real numbers. I can plug just about any number in for x, but my range, notice it doesn't ever equal 0, but it's going up. Y is greater than 0. Notice it's not equal to. Again, if you'd like to use the interval notation, remember this time you'd have to use a parenthesis on the 0 side and then your infinity symbol. For our logarithmic equation, the parent function for this one is y equals log. We're going to use a specific case again with a tiny 2 of x. Again, just like this one, this number could be just about anything, but we're looking at some specific cases to do our transformations with. For this one, something that's important to know about the logarithmic and the exponential equations are what we call inverses. For inverses, we take the x and y values and we switch them. So for my table here, I'm going to do the same points except switched. So I can start with 1/2, that's going to be -1. 1 is going to be 0. 2 is going to be 1. 4 is going to be 2. Again, those are the ones I want you to know. You could put the other ones on here if you wanted to. Let's plot this one. Here's 1/2, -1, 1, 0, 2, 1, 4, 2. If I wanted to put 8, 3, I could. This one is going to look, like I said, very similar, except it's kind of going in the opposite direction. This one also has an asymptote. This time it's a vertical asymptote. Notice the similarities between this graph and this graph. This graph has been reflected over the line y equals x to create that inverse equation. That's something that's true of inverses. Again, we'll talk about those a little bit later on in the year. So here's our asymptote. Let's identify the domain and the range. If we switched our x and y values here to create this inverse graph, then what's going to happen to the domain and the range? They're basically going to switch. Your range this time is going to be all real numbers. The domain is going to be x is greater than 0, or again, if you prefer interval notation, from 0 to infinity. I would also like to point out the similarity between this graph and our square root graph. Notice the square root graph actually touches here at 0 and stops. For the logarithmic graph, it continues on infinitely down. So pay attention to some of the differences between this. You are going to have a quiz over this material sometime during this chapter where you're going to have to recreate this whole table on your own from memory, including the names. So it's a good idea to start practicing and studying this stuff. You're also going to have a quiz tomorrow over matching just the name to the graph to the equation. So you might want to start studying those. That's what we're going to do some in class tomorrow.